Namaste. Welcome to the next video of Machine Learning Practice course. In this video, we'll implement linear regression models for housing price prediction. So far, we built different kind of linear regression models in bits and pieces for housing price prediction. In this collab, we'll combine all those models and give you a holistic picture of how different regression models perform for this task. Specifically, we'll build linear regression model with normal equation and iterative optimization. Then we'll go on implementing the polynomial regression followed by regularized regression models using Ridge and Lasso regression. We will set regularization rate and polynomial degree with hyperparameter tuning and cross-validation. Finally, we'll compare different models in terms of their parameter vectors and mean absolute errors on train, development set and the test sets. We begin by importing the classes that we need and the utilities from different sklearn modules. For example, we are going to use different regression models, hence we have imported multiple regression classes from sklearn.linear_model module. For example, we have imported linear regression, Lasso, Lasso CV, Ridge, and HGD regressor. For creating a baseline, we have also imported a dummy regressor. And in one of the last collabs, we have seen how to build baseline models for linear regression task. Then we have also used polynomial features from sklearn.preprocessing modules that will be used for building polynomial regression models. Then we have various metrics and utilities from model selection that we have imported, and we will be using them to build different linear regression models and select appropriate models for the housing price prediction task. We'll be doing all this processing through pipeline. So we begin by setting a random seed to a number of your choice. So here we have used 306 as a random seed. We'll use shuffle split as cross validation with 10 splits, and we'll set aside 20% examples as test in each fold. We'll use California housing dataset for this demo, and we'll load this dataset using fetch_California_housing module in sklearn. We'll be loading this dataset as data frame, and we request this particular API to return XY pair. So this API returns features and labels in form of data frames. We'll first perform the training and split. Followed by, what we'll do is we'll take this training data and we'll split it further into training and development set. So here we are going to hold out the test set and we will not show it to the training in any form. This test data will be used for evaluating the performance of the model. So now what we'll do is we'll build a linear regression model followed by linear regression model with HGD, then polynomial regression model, ridge regression model, and lasso regression model. Then we'll also perform hyperparameter tuning for ridge and lasso. So this hyperparameter tuning also includes hyperparameter tuning for the degree of the polynomial regression. Now we are going to follow a specific pattern in each of these linear regression models. We'll be using pipelining, and first we'll be doing a feature scaling. In each and every pipeline, we will first implementing feature scaling that will help us to get all the features on the same scale. Here we use standard scaler as a feature scaling mechanism. In the first pipeline, we are using linear regression class, and this linear regression essentially implements the normal equation in order to learn the parameters of the regression task. Then we'll perform the training of this pipeline through cross-validation. So the cross-validation based training, it ensures that we have a robust training with different folds that we get in cross validation. So here we specify the linear regression pipeline as the estimator for cross validation. We have combined training features and labels. We are going to use shuffle split CV as a cross validation mechanism. We'll be using negative mean absolute error as a scoring mechanism for this cross validation. In addition to that, we are setting the optional parameters of returning the training score and estimator to true. So this will give us the training score in each fold of cross validation, and we'll also get the estimators that were learned on different folds. We'll convert these scores into error and we'll print the errors. So we can see that when we run this, we get the mean absolute error for linear regression model. On training set it is 0.53, and on test set it is slightly lower, which is 0.527, which is very close to the training error. Here we can see that both training and test error are close, but they are not low. This points to underfitting. We can address the underfitting problem by using polynomials of higher degrees. Before building a polynomial regression model, we'll also use iterative optimization method to train the linear regression model. Here, instead of linear regression, we use HGD regressor as an estimator. We set the max iter based on the best practice that we saw in the last collab. So we basically set maximum iteration such that HGD is able to see at least 1 million examples. And around 1 million examples, empirically it has been found that HGD generally converges. We are also using early stopping, and for early stopping we are setting the tolerance to 10 raised to minus 5 with validation fraction of 0.1, and we call the early stopping if there is no change in the error for 5 consecutive iterations, and that change is measured up to some tolerance value which is specified over here. Then we are going to use average HGD. So each time we set the weight updates to the average of all the weights, since HGD has seen 10 samples. We again train this model through cross validation. And now you can see that here also we get comparable results on the training and test set. So the error, which is mean absolute error, is kind of comparable to what we got in the linear regression model. So here with normal equation the error was 0.53, and with HGD it is slightly higher, which is 0.56. So we know that HGD has bunch of hyperparameters that needs to be tuned, and we can probably get this error down by tuning those parameters. Next, what we do is we train a polynomial regression model with degree 2, and we'll use a concept of validation curve to find out the right degree for polynomial model. So here we have 3 stages now. We have first stage, which is polynomial transformation. So here we transform the input set with polynomial model with polynomial features of degree 2. We perform standard scaling on the transform matrix through polynomial. So now the standard scaling is applied to the feature values that are obtained through the polynomial transformation. And after feature scaling, we basically are using the linear regression, which uses normal equation to train the parameters of the model. We again train this pipeline through cross validation as before, and we record the training and test errors. So here you can see that as soon as we use a polynomial model of degree 2, the error has gone down to 0.46. So training error is 0.46 and the test error is 0.48. And since we are performing cross validation, we also get the standard deviation on the error. So you can see that standard deviation is also pretty low. So what happens is that because we are doing cross validation, we are going to train this polynomial regression pipeline on multiple folds, and on each fold we get the estimates of test error and under training error. And what we have done here is essentially we have essentially printed the mean value of the training error that was calculated on each fold along with the standard deviation, and the same thing was done on the test set on the test error. Remember, here the test error is calculated on the development set. It is not calculated on the true test set, and the true test set is actually held back. So here, because we are giving the combined training features, which has got training plus development set and cross validation, what happens is that one of these folds is set aside as test, and this test error is calculated on the holdout set in the cross validation. And hence, since we are using a shuffle split cross validation with 10 folds, we basically get 10 errors, 10 training errors and 10 test errors. And what you see on the screen is the mean of training and test error and the standard deviation, which is calculated from those 10 numbers that we get from the cross validation. Alternatively, we can also use only interaction features in polynomial. So if we are using only interaction features, what will happen is it will exclude all the higher order degree features for individual features, and it will only include the interaction features. So when we do use interaction features and we perform the training through cross validation, what we see is we get mean absolute error of 0.47, which is slightly higher than what we obtained when we are using all polynomial features of degree 2. We need to figure out the degree that gives us the best performance on the regression task, and for that we'll use validation curve API from sklearn. We give the polynomial regression pipeline as an estimator as a parameter to validation curve, along with the feature matrix and the label matrix and the name of the parameter on which we want to perform the validation task. So here the name of the parameter is poly underscore underscore degree, and this is the way we can specify the parameters in the pipeline. So since we are using pipeline and the name of the stage is poly, so that's why there is poly over here, and this is the parameter of this particular stage, which is the degree of the polynomial, and the range is specified to this degree list. We are going to use shuffle split as a cross validation, and we'll be using negative and absolute error as a scoring mechanism. So we convert the scores that are obtained from validation curve into errors, and we plot the error for each degree. So we have degrees on x-axis and we have error on y-axis. So you can see that there are 5 values for degree 1, 2, 3, 4 and 5, and we have 2 lines here, one corresponding to the training error. The blue one corresponds to the training error and the red one corresponds to the test error. And you can see that at degree equal to 2 we have the least value of the test error, and beyond this point test error starts going up. So this particular region shows some kind of overfitting, and probably the degree 2 is probably the appropriate value for the degree, because at that value both training and test error are close and they are the lowest among the 5 different values that we have tried. The polynomial models have a tendency to overfit. We have studied this multiple times in this course so far. So one of the remedy for fixing the overfitting problem is to specify or is to use some kind of regularization. Here we are going to use ridge regularization. So we have built a pipeline. So instead of linear regression, we are going to use ridge regression. So ridge regression is nothing but linear regression with regularization terms added to it. So we are setting the regularization rate alpha, and again reminding you that this alpha is different from what we were discussing in machine learning techniques course. In machine learning techniques course, we use lambda to denote the regularization rate, and we use alpha to denote the learning rate. But in sklearn, alpha is used to denote the regularization rate instead of lambda. So whenever you see alpha, you have to draw correspondence to lambda in regularization. So we are going to use the regularization rate of 0.5. We train the ridge regression pipeline in a cross-validation manner, and we record the training and test scores. We convert the training and test scores to errors, and we calculate the mean and standard deviation of the error across different folds in the cross-validation. So we get the training error of 0.48 compared, so this error is higher, slightly higher than what we obtained in polynomial regression, and which is going to happen because we have now added an additional regularization term. So now this regularization term, we have this lambda, or the regularization rate, which is specified as alpha in case of sklearn, and we need to tune the value of alpha and find out ideal value of regularization rate that gives us the optimal performance of this particular ridge regression estimator. So we can tune the value of alpha, or we can find the value of alpha through multiple ways. We can either use this CV or other general hyperparameter tuning like grid search CV or randomized search CV. So we'll use here the Ridge CV method to begin with, and in order to use Ridge CV method, we need to specify the value of regularization rates, or alpha. So here we specify a list of regularization values to be tried, and we train the model with the combined training features and labels. So we can find out what is the best score that we obtain through cross-validation. That can be, so we can call the best underscore score underscore member variable of Ridge CV estimator in order to find out what is the best score that we obtained with the best value of alpha, and that is 0.47, and this score is now, this error is now lower than what we got from the baseline ridge regression model, where we had set the value of regularization rate to 0.5, and the best value of regularization rate that we found through Ridge CV is 0.0078. We can also perform this procedure through cross-validation in order to get more robust estimate for alpha, and we can also understand what is the variability in alpha when we train it in a cross-validation manner. So we actually leave this, we have written code over here, but we leave this as an exercise for you to experiment with this particular portion of this collab. We also show how to perform the same hyperparameter tuning through more general way of hyperparameter tuning method, which is grid search CV. So here, instead of grid CV, we use Ridge, and we actually specify the parameter grid. Here there are two sets of parameter that we want to try. One is we want to tune the degree of the polynomial features, and we also want to tune the value of alpha, or the regularization rate. So we specify the parameter grid where we want to try the degrees, which are 1, 2 and 3, and the value of alphas from 10 raised to minus 4 to 0, and we want 20 different values in this range as values of alpha to be tried. Then we define grid search CV with Ridge grid pipeline as an estimator, the parameter grid which is specified over here, shuffle split cross validation using negative mean absolute error as a scoring mechanism. Then we train this particular grid search CV with the combined training features and labels. And remember, this combined training features has training and development set. So we see here the specification of the parameter grid. The value of the degrees that we are trying is 1, 2, 3, and the values of alpha or the regularization rates. These are the 20 different values that will be tried out. Now what we'll do is we will find out the best parameter from the cross validation. So we can get this best parameter through the best underscore index underscore member variable. So this is the index of the best parameter in the list, and we can find out what is the mean training error and the standard deviation on training and test errors. So we can see that for the best value of the hyperparameters, we obtain the training error of 0.46 and the test error of 0.47. Now you can see that these errors are lower than the base ridge regression model that we tried out. So the best error that we obtained is 0.473. And we can also see what are the best parameters. So we found out the polynomial degree of 2 and the value of regularization rate of 0.0078. We obtained the optimal performance on the cross validation set. Next, we try more aggressive regularization, which is lasso regularization. Here we set up the pipeline with lasso as a regularization, and we have set the regularization rate by hand to 0.01. So we train this lasso with cross validation, and we can see that the error is pretty high, which is 0.52 compared to what we obtained through ridge regression and through polynomial regression. Remember, here we are also using the polynomial features. Now what we do is we will perform hyperparameter tuning for the degree of the polynomial and the regularization rate in lasso. We use pretty much the same values as with the ridge regression in the parameter grid. We performed the grid search and found that the best mean absolute error on the training set is 0.46 and on test set it is 0.48. Now you can see that these errors are much smaller than what we obtained in the base lasso estimator, and these errors are comparable to what we obtained to the errors that we obtained in the ridge regression case. And you can see that the best values of the parameter, the alpha value was found to be 0.0001 and the degree, the best value of degree was 3. For this combination of the parameter set, degree of 3 and value of alpha, which is regularization rate, which is 0.0001, we found that the lasso regression has the optimal performance on the cross validation set. Finally, we will perform the hyperparameter tuning of various parameters in HDD regressor. So you can see that if we use HDD regressor with elastic net penalty, so elastic net penalty uses both L1 and L2 regularization. So the base case of elastic net penalty with all other hyperparameters set to their default values, we obtained not so great errors. So these are very high errors compared to what we have seen so far. So what we do is we perform a hyperparameter tuning on HDD. But instead of using grid search CV, we are going to use randomized search CV here for different hyperparameters. So in randomized search CV, we need to specify distributions for each hyperparameter. So here we are specifying distributions for different hyperparameters that we want to tune. So you want to tune the degree of the polynomial features, and we want to try 3 degrees, 1, 2 and 3. We also want to try different learning rate strategies in HGD regressor, and those are basically strings which are constant, adaptive and inverse scaling. For L1 ratio, so L1 ratio is what we specify in elastic net regularization. Remember, the elastic net regularization is a convex combination of Ridge and Lasso regularization, and we specify what is the weight that is assigned to L1 or Lasso regularizer, and the weights that will be assigned to L2 or Ridge regularizer will be 1 minus the weight assigned to Lasso regularizer. So here we want to try L1 ratio uniformly between 0 to 1. The value of eta 0, which is initial learning rate in HGD regressor, we want to draw that from log uniform distribution with the range 10 raised to minus 5 to 1, and the power from the uniform distribution from 0 to 1. So this power controls how the learning rate will be reduced from one iteration to the other in case of inverse scaling. So we specify the random search CV object with polynomial HGD pipeline as an estimator, and that pipeline is what we have set over here. It has got polynomial features followed by feature scaling and an HGD regressor with elastic net penalty. So we specify the random search CV with poly HGD pipeline as an estimator, the parameter distributions for various hyperparameters. We want to run randomized search CV for 10 iterations using shuffle split cross validation, and we are going to use negative mean absolute error for scoring. So number of iteration is a way of controlling how many times we want to perform the randomized search. So this is one way of controlling the budget or the time that we spend in performing the parameter search. So we basically use the combined feature matrix and labels for training this randomized search CV hyperparameter tuning strategy. So we got the best score of minus 0.52, and then we have gotten the best parameters where polynomial degree is 1, the initial learning rate is 0.00015, the L1 ratio is 0.54, learning rate style is constant, and the power underscore t to be 0.49. So the best estimator can be accessed with best underscore estimator underscore member variable of the randomized search CV object. So we can, now that we have trained multiple linear regression models, we can look at the weight vectors produced by different models. So since we are using polynomial regression, we'll first list down the features that we obtained through polynomial regression. So you can see that these are original features. This is one that we add in polynomial regression, and these are the interaction features. So here we are combining median income and house age. So this is how different features are combined. And here we are mostly using only interaction features. We are not using higher order degrees of each of the features. And you can see we can see the variation in the weights of different polynomials. So you can see that the point to note is the range. The range is quite high. So something like average occupancy in some folds, the weight values given to average occupancies are quite high. We can fix it by through ridge regression, where you can see that the range is now more uniform around 0. It is between -30 to +30 rather than being skewed in earlier case. And in this case, we are using, in case of ridge regression CV, we are using the polynomial features which also include the higher degrees of individual features. So you can see that this is a square of medium income. This is the cross of medium income and house age. This is the square of the house age. So we are using polynomial features in case of this estimator, which also includes higher order degree features of individual features. Finally, we can compare the performance of different regression models on the test set. And performance on the test set, this is the true test set that was held out, that was not at all exposed during the training. And this will give us a reasonable estimate of how our models will perform on the future data. So we start with the baseline model, which is a dummy regressor that gives us the mean absolute percentage error of 0.53. Note that we are using mean absolute percentage error as the error metric, and that error metric turns out to be 0.53 for baseline model. When we use linear regression with normal equation, we get the mean absolute error down to 0.32, and when we use HGD, we get it down to 0.31, slightly lower than what we obtained through the normal equation route. And again, remember, this is the best estimator that we obtained through randomized search CV. For polynomial regression, if we use polynomial regression, we get it down to 0.28, and if we use ridge regression, we are getting it down to 0.27, and with lasso it is 0.28. Again, it is slightly lower than what we obtained in polynomial regression, but again, remember, here we use polynomial features of degree 3 because that's what we found through the grid search CV for the lasso pipeline. So you can see that among these different classifiers, ridge regression seems to be doing pretty well, and we can use ridge regression for future prediction because it has given by far the best performance than the other regression methods. So here in this collab, we trained multiple linear regression models on housing dataset. We set their hyperparameters through hyperparameter optimization methods like grid search CV, randomized search CV, and some specialized cross validations like ridge CV and lasso CV. So we retrained the models with best values of hyperparameters and evaluated their performance on the test set. We did not do this explicitly, but this happens as part of randomized search CV and grid search CV procedures. And this particular collab is an example of how most of the real world problems are solved. So we started with a simple baseline model like dummy regressor, and then we went on building more and more sophisticated models. So this particular collab serves as a template of how you can build regression models for the task at hand.